Good morning, everybody. We are working in the middle of chapter 7. In fact, we're getting toward the end of it, and we're talking about hypothesis testing. Let me show you and share with you the calendar as we get going here this morning. Oops, that's not the calendar. Where is the calendar? Okay, I think I have everything out here in Canvas for you now, from now to the end of the semester, which is just 2 weeks away, right? We have 2 weeks. Then we have sort of a week of no class during finals week, and we're going to take our test on Thursday, the 7th. So our plan is finish or do most of chapter 7 today, finish 7-4 maybe on Tuesday. Start talking about chapter 9. We're going to talk about chapter 9 for the rest of the time. And then we'll take the chapter 9 test on Thursday, whatever day that is. Is that the 30th, maybe 31st? Right at our last day of class. Then you'll have a couple of days off, and then we'll have the final on Thursday, the 7th. And that will be, that's when it was scheduled for. But things are a little bit different because some people have chosen to extend their classes 2 weeks due to our interruption. Since we got right online, I decided that we didn't probably need to do that. So we're going to wrap up during the regular finals week. Other classes are still going to be continuing on though. So the finals week, which is normally a special schedule, there might be some conflicts there for you personally. What I'm going to do is I'm going to open the test at 8 in the morning, and you're going to need to get it done by 12 o'clock. Okay, so 12 noon. So you got 4 hours. You're certainly welcome to just come at our regular time and get started. You can, start a little later if you feel like you're not going to need that much time, or if you have a conflict. And if for some reason you have a big conflict, as in you can't come anytime during that time, or maybe you can only come for an hour, then you got to let me know so we can work something else out. So that's the plan. We're going to do we're going to go along, like I said, finish chapter 7, finish chapter 9, and then take the test on May 7th, and then we're done. Questions about that? Okay, well, not seeing any questions on that. Let me also share with you this announcement that I sent out. So hopefully you got this. If you didn't, well, here it is again. And I can see if there's any questions on it. The school, actually the whole district, so all 10 colleges, the district has decided that they are going to change the grading, the default grading scale. And so they're going to change all classes to credit, no credit. Basically, that means that if you have a C or better, you're going to get a P. And if you don't have a C, so if you have a D or F, you're going to get no credit, which turns out on your transcript to be a Z grade. I read some of the reasoning for this. Some of it sounds really good. I mean, I'd rather have a Z no credit than maybe an F on my transcript, because the PZ grades don't count towards your GPA. There are some problems, however, with going to pass, fail, or PZ credit, no credit grades. And that is that if you have any special circumstances, like a scholarship, if you're in the honors program, if you're an athlete, then sometimes people don't accept these pass, fail grades as being acceptable. They require a letter grade. Generally speaking, transfers like to ASU or other places won't take a pass-fail grade either, although the school has been assured by at least our local state colleges that they're going to take them for this semester because of the interruption from COVID. Me personally, my recommendation would be that if you have a C or better, you should probably take the letter grade. And if you have a D or an F, you should probably take the no credit. That would be my recommendation. You should look into it. If you have any questions about it, there's a link there to some policies. And then the only big change is that, of course, when you signed up for this class, you were getting a letter grade. But now by default, you're going to get a credit, no credit grade. So unless you tell me otherwise, you're going to end up with credit, no credit. So if you want a letter grade, then you got to go on here and fill out this little Google form, put in your name, choose our class, and select letter grade. Okay. And if you do that, then when I'm filling out the grades, I'll take a look on the list. And if you ask for a letter grade, then you're going to get one. Okay. Questions about that? Okay, you can find the links and the form and everything in the announcements right here in Canvas. So go click on your announcements or check your email. It should be in your email. And then that's it for calendar and administrative stuff. Any questions about calendar or administrative stuff? Bradley's saying nope, he's good. I got everybody else kind of listening in. There's a chat one. Let me see, I have to stop sharing to read it. So I've got nope in the chat. So if you do think of some questions about those things, please let me know. If you sign up for one kind of grading and you change your mind, you have to make your mind up by, I believe, April 30th. So you have to have your selection made by then. But if you do change your mind, just fill out another, go to the form again and submit another response. And then I'll take the most recent one. Okay, well, let's talk a little bit about chapter 7. Last time you guys were here, we were talking about hypothesis testing, and we were looking at the situation when we knew the standard deviation of the population. Today, we're going to look at hypothesis testing when we don't know the standard deviation of the population, and I think we'll maybe even go on and look at hypothesis testing for a population proportion, as well as testing for the mean. So essentially what it comes down to is this. All right, we're going to be, this was 7.2 was testing for the mean, or testing the mean. Right, and that's mu. So what we're going to do is we're going to say, I know the average of a population, and I suspect it either has changed or maybe I don't believe what was advertised. I'm going to take a sample and I'm going to say, based on this sample, does it look like the mean is different from what they said? Okay, that's what we're going to say. So one example, we talked about it last time, was miles per gallon in the car. You go to buy a car, it says right on the window that it gets 40 miles a gallon. You suspect maybe that's a little bit high. So you take a sample of 20 cars and you look at the average. And if the average is significantly less than 40, then you're likely to say, hey, what are you doing? You've got the wrong number in the window. You're trying to rip me off. Okay, that's kind of how hypothesis testing works. There are two situations. There's the situation when we know, right, when we know the standard deviation of the population. Okay, and unlike confidence intervals, where we're trying to decide something about a population you don't know much about, with hypothesis testing, we generally know the mean and the standard deviation of the population, and we're testing to see if it's changed. Okay, so we generally do know this, or at least more often. We know that the data is normally distributed, or we take a sample size greater than or equal to 30. Okay, so if the data is normally distributed, then the distribution of all the possible samples, the sampling distribution will be normally distributed, and we can use the area under the normal curve to find the probability. The same is true if we pick a large enough sample. So if the population is normally distributed, the sample distribution will be normally distributed. Or if we pick a big enough sample size, by the central limit theorem, it turns out that the sampling distribution will still be normally distributed, or at least approximately so, to a few decimal places, and we can make a pretty good estimate. Okay, so then, what does it say? Then the central limit theorem I'll call it CLT, says that the mean, the distribution of all the sample means will be normally distributed, okay, with a mean, the mean of the distribution of sample means equal to the mean of the population, and the standard deviation of the distribution of sample means, sometimes called the standard error, is equal to the standard deviation of the population divided by the square root of the sample size. Okay, so then what do? We take our sample, we look at the sample mean. That gives us a point estimate. And then we say, how far away from what we expected is this? If it's far enough away, then we're going to reject the null hypothesis and go on about our business. So next we would write the null and alternative hypotheses. The null hypothesis is that the mean is, what we said it was. Okay, so the mean is whatever it was claimed. Now we could test left-tailed or right-tailed and test whether the mean is greater than or equal to or less than or equal to here as well. The alternative would be that the mean is not what we claimed it to be. Okay, so what are we doing? We're claiming that it gets 40 miles to the gallon. We're taking a sample. If the average is way more than 40 or way less than 40, then we're going to reject this idea that it is 40 in favor of the alternative. That's how the test goes. So what do we look at? We look at the test statistics. So the Z for our X bar is our value minus the mean divided by the standard deviation, right, of the sampling distribution. Some people like to find a Z-score and then use the area under the standard normal curve. Some people like to just let their calculator calculate the Z-score directly, and they just put in the actual values. So whether you standardize first or don't standardize, sort of up to you and the technology that you're using, right? And then we find our p-value, and our p-value is equal to the probability that Z, right, is greater than this value. Okay, so where's our value Z of X bar? In other words, we find the area under the curve, right, that is outside of this Z test statistic that we've computed. Right, so essentially the picture looks like this. We got the distribution of sample means. Okay, its mean is centered right on the mean. Its spread is given by the standard deviation of the population divided by the square root of the sample size, and we calculate some Z. The question is, how much area is left? If this is really small, then this is pretty unlikely to have happened by chance, in which case we would say that the mean is probably not what they say. So the question is, how do we decide how far over is far enough? Okay, and before I do that, and of course to find this probability, most of us have been using the TI-84 and typing something like normal CDF, right? And then in this case, since we're going to the right, we would say, well, let's see, our hypothesis test was equals. So not equals means it could be too high or too small, right? Too big or too little. And so what we'd have to do is double the area to the right of our Z. So we put in our Z and we go to the right, right? And we find that area. Of course, you can find that area looking in the book using other tools as well, but that's how you do it on a TI-84. Okay, now that we've found how much area is left, we need to decide, is it, enough? Okay, is it significant? Generally, the problem is going to state the level of significance, and we call that alpha. So we might say alpha is at the 1% significance level. In other words, we need there to be less than 1% of the area left. You need to be far enough over that this p-value is less than 1. Okay, and if that's true, we reject the null hypothesis. The other way that we might do it is look at a critical value. The critical value, right, or Z sub C, we've been calculating, is the cutoff for 1%. Now, since this is a two-tailed test, we would have to find where there's only 0.5% left on this side. Okay, so to do that, and the TI, we're going to say inverse normal, and we're going to go 995, and we're going to find the cutoff. Okay, and I think that's 2.576, I think. Okay, so that means if I'm more than 2.5 standard deviations over here, then I'm going to say the test is statistically significant. So there's two ways to do it. One is called p-value testing, where we get the p-value and we compare it to the level of significance. And the other is critical region testing, where we get the critical value and we check to see if it's far enough over. Right? And so those are the two ways that we conclude the test. And then conclusion is reject H0 or fail to reject. Notice that the conclusion is not reject H0 or accept it as true. Okay, this hypothesis test is not able to prove that the mean is what we say it is. It's only able to prove that it isn't. Because think of what would happen. If we're way over here, that's unlikely to happen by chance, in which case we would say that maybe the mean isn't where it is. But if it's not over here, that means it's somewhere in here. Well, what does that mean? That's exactly what we would expect it to be. So the conclusion is there's enough evidence to reject the null hypothesis, or there isn't enough evidence to reject the null hypothesis. Those are the two conclusions of the test. Basically, it's like a trial. You would assume somebody's innocent until they're proven to be guilty. And so then the lawyers bring their case, right? They bring all the facts, and they try to provide enough evidence beyond a reasonable doubt that the person committed the crime. Okay, and so what's the conclusion? Well, if there's a reasonable amount of evidence, right, then you conclude that they did it, okay, and that they're not innocent. So our null hypothesis is that they're innocent, but if there's enough evidence, we reject the null hypothesis and conclude that they're guilty. On the other hand, maybe the lawyers and detectives and investigators don't do a very good job on the case, and they don't bring enough evidence. And so then what happens? Well, then there's not enough evidence. So you don't find the person to be innocent. What you find is that there's not enough evidence to prove that they're guilty. So they may very well be guilty for all we know, but we've assumed that they're innocent. You can't prove that they're innocent if you're already assuming that they're innocent. I mean, they're innocent unless they're proven guilty. Okay, so the conclusion would be, I don't have enough evidence to show that they're guilty. Or I do have enough evidence to show that they're guilty. At the end of the trial then, if they're let go, we don't know if they're innocent or not. Okay, all we know is that there wasn't enough evidence to prove that they were guilty. And the same is true for hypothesis testing. Okay, and so those are the conclusions. All right, that was section 7.2. That's the recap of 7.2. Essentially, those are the steps for hypothesis testing. And of course, for 7.2, we knew the standard deviation of the population, right? Which is important because if we're going to use the area under the normal curve, we're going to have to calculate its spread. And to do that, we need to know sigma. Now, it could be that if we're calling into question the mean, if we're testing the mean, then it could be that we don't trust the standard deviation of the population either. So that takes us to the next section, right? That gets us to 7.3. So in 7.3, we're going to test the mean. But now we're going to have sigma unknown. Okay, so if we don't know sigma, right? If we don't know sigma, then what we're going to do is we're going to use the standard deviation of our sample to approximate it. Of course, when we approximate sigma, we're introducing additional error. And the error shows up in the distribution of the sample means. Right? They're no longer normally distributed. In fact, they turn out to be what we call student T. They follow a student T distribution. And you can read the history of Gossett and student T distributions in the book if you like. So everything else is the same, right? Here's what we would need to know. We would need to know that the values are normally distributed, or, right, we take a sample size greater than or equal to 30. Okay, greater than or equal to 30. If that's true, then, and it's, I think we still call it the central limit theorem. Okay, the central limit theorem says that the means of all of our samples are student T distributed right, with a mean that's equal to the sample mean and a standard deviation that's equal to S over the square root of n. Okay, so we're going to approximate the standard deviation of the population using the standard deviation from our sample. So this is the sample standard deviation. Questions so far? Beautiful. Now, it turns out that this isn't quite that simple because the student T distribution isn't just one curve, but rather a family of curves. And so if you take a small sample, then there's a lot of error in this estimate for the sample standard deviation. If you take a big sample, then this is a better estimate. And so the distribution has to account for the fact that we get a better and better estimate as we take a bigger and bigger sample. That's reflected in something that we call the degrees of freedom. Now for a one sample test, the degrees of freedom, which we call DF usually, is equal to 1 less than the sample size. So it's got a small number of degrees of freedom for a small sample and a lot for a big sample, basically. Now, what that means, essentially is that the student T distribution starts to look more and more like a normal curve as the sample size goes up. Okay, in other words, there's less error in our estimate as we get a better sample. Okay, so for you, what that means is we're just going to push a different button. We're going to look at the area under the student T curve with n-1 degrees of freedom, as opposed to looking at the area under the standard normal curve. There's a bunch of math in the background that your calculator or the back of the book is doing to actually graph this curve and find the area under the curve. But for us, we're just going to use the book to find the area. Okay, if you want to find areas by hand, then you're going to have to do a little calculus, right? That's Calc 2. Okay, so we calculate the test statistic. So the test statistic we call T this time instead of Z. And we find it by looking at how far away from the mean we are divided by the sample standard deviation divided by the square root of sample size. Okay, so this is the exact same calculation. Now, this is our normalized test statistic. So if you want to look at the area under the standard t-curve, then we have to normalize. If you want to let the calculator do this step for you, then you're going to just put in the values of the mean and the standard deviation into your calculator when you do the calculation. And then we find our p-value equal to the probability that t, right, the t we calculate is greater than this calculation that we just made. In other words, what's the chance that we get a t that's really rare, that's way over there? On our curve, it looks something like this. Notice that the student t-curve is flatter and doesn't come down to the axis quite as quickly as our normal curve. That means that there's more area out here in the tails. The additional area out in the tails corresponds to the additional error that we've introduced by estimating the sample standard deviation, estimating the population standard deviation using the sample. So this is the distribution of all the sample means, and it follows a t-curve with n-1 degrees of freedom. Okay, so it's centered, the mean of our curve is centered at the mean, and the spread, right, our spread is now equal to S over root n. And the question is, if I get a fairly extreme value, we'll do two-tailed again. The question is, what's the chance it's going to fall way over here or way over here? In other words, if we're talking about the car example, and I'm talking about it being advertised at 40 miles a gallon, what's the chance it's way down at 10 miles a gallon or way up at 80 miles a gallon? Okay, and you would have to say, pretty unlikely, right? Pretty unlikely. So what do? We find this area. And of course, this p-value corresponds to this area. If it's two-tailed, then we double the p-value. If it's one-tailed, then we just have the area on one side. Okay, so how do we kind of wrap that up and find the area? On your TI-84, right, you're going to, instead of saying normal CDF, did I write that down over here? Yeah, we doubled it too. So our p-value was 2 times the normal PDF. Now we're going to instead, here, let me get it out here so you can see it. Okay, under distribution, we found the normal PDF. We come down here to the T CDF, okay, for the T curve. And so we find 2 times the T curve, it's the cumulative density function, and we're going to find, if it's on both sides, then we need to find the area, you know, from that is bigger than this. So we're going to put in our T value, right? And we're going to go all the way up to as big as the calculator can get, 1E99. Okay, so then the last step is concluding the test. So now we found this p-value, and we want to know if it's statistically significant. So we look at the test, and we get an alpha. In this case, maybe our alpha was 5%. So what we're saying is our p-value, right, smaller than 5%? So is there less than a 5% chance that I fell over here? And if so, the test is statistically significant and we reject the null hypothesis. The other way that we sometimes test is critical value testing. We find a T sub C that cuts off a particular area. In this case, it would cut off 95% of the area would have to be on the inside, right? That means that there would be 2.5% over here and 2.5% over here. So to find our critical value, instead of using inverse norm, we're going to use inverse t. And we're going to say, I want, in this case, 975, because I'm looking at just the stuff on the one side. And we have to tell it the number of degrees of freedom. And so we'll get this critical value. And then to conclude the test, we'll say, did our test statistic fall further away from the mean than our cutoff, our critical cutoff? If it did, we say the test is statistically significant. We reject the null hypothesis. And then we're done. So the conclusion is that we reject the null hypothesis, or we do not reject the null hypothesis. In other words, there's enough evidence to say that it's different from what we claimed, or we don't have enough evidence. Okay, we don't have enough evidence based on this test to claim. And that's the conclusion, and then that's it. That's the whole summary of hypothesis testing of the mean. So I guess all that's left to do at this point would be to try, maybe try a couple of problems, and then let you go practice a few on your own, make sure that you've got it down. And then on Tuesday, I think I'd like to come back and do hypothesis testing of a proportion. And so that'll be the last section, section 7.4. Questions? Doing the homework, it was easy to understand the reject or fail to reject part, but enough evidence, not enough to support is confusing still. Okay, so having enough evidence to reject is just the same if you are far enough over. So reject is going to happen, right? If you, having enough evidence means that your test statistic fell far enough over. It was unusual enough, or it was enough standard deviations away from the mean. So those two things turn out to be just language, okay? There's no math going on there. It's just language. If we reject, then we say that it was statistically significant and there is enough evidence, right? If we don't reject, then our test statistic fell in the middle here somewhere, and we say there's not enough evidence to support the claim. And then that's it. Let's try an example and see if we can do one example out of the book. So what I did is I brought the book up. Let me see if it's still up. Sometimes it shuts down if I don't go fast enough. Here's the book. Okay, so it's still here. So here's example 4 out of the book. It's on page 380. And because it's hard to see on that little screen, I'm just going to copy down the data, the info, and then we can, then I'll stop sharing. So here's the claim. A used car dealer says that the mean price of used cars sold in the last year is at least $21,000. So let's get some info written down here. This was example 4 on page 380. And the claim is, so, basically what you would do is go through all the steps that we've gone through the last couple of times. And how many of those steps you actually have to write down is going to depend on how much you can do in your head. So at first, I would write down a lot more detail. And then as I got a little bit more comfortable with it, and I could sort of make the graphs in my head and kind of see what's going on in my head, then I would probably write down less detail, okay? And eventually, you might just read this and type the numbers straight into your calculator and then just push the button without drawing anything. Now, when it comes to be test time, you're welcome to do that because you just have to, choose the multiple choice anyway. But if you would like me to, evaluate it for some partial credit, then you got to put a little work down. So even if you can sort of jump right to the calculator at first, for your partial credit, you should at least write down, hey, what did I type in my calculator? Or make a little picture of the normal curve so I can see what's going So the more you share with me, the better chance I would have to find some partial credit for you if in the end you end up with the, the final answer is a little bit wrong. Okay, so the null hypothesis. The null hypothesis is that it's at least $21,000. That means that the mean is greater than or equal to 21,000. That makes the alternative that he didn't sell that much, or the average price of cars was less than 21,000. Okay, so to test to see if he made this much in sales, he's going to take a sample of 14 used cars. So I don't know, maybe he pulls receipts, right, out of his file cabinet or something, and he says that N was equal to 14. Okay, and in that sample, we ended up with the sample mean. Now, if it gives you the sample mean, awesome. If it doesn't give you the sample mean, you would have to take the 14 cars, the prices of the 14 cars, add them up and divide by 14, right, and find it yourself. In this case, it had a mean of 19,189 and a sample standard deviation of 2950. And then it says, is there enough evidence at the alpha equals 5%? So we want to be at the 5% significance level, or we'd like to be 95% confident. The last thing it tells you is that the prices of the cars are normally distributed. Okay, so since you can't see my little stuff, I'm going to stop sharing. I think we got all the info. Here's the setup for the problem. And the question is, can we test this hypothesis and find out if this mean, look at this is 19,000. That's quite a bit less than 21. So we're saying, is this enough evidence? Is this far enough, right? Is it enough smaller than 21 to be statistically significant, to reject this claim that you made that the average price of cars was 21,000? Okay, so we would expect, since the prices were normally distributed, that some are going to be a little more than 21,000, some a little bit less. Okay. The question is, if you're a lot less, then that would be pretty unusual given that these are normally distributed. So is 19,000 enough less that we can say it's statistically significant at the 5% significance level? Or is there less than a 95% chance of this happening by chance? Okay, that's basically what it comes down to. The first decision that you need to make is whether or not we can use the sample distribution, the areas under the sample distribution to find this probability. And that will only work if the samples are normally distributed or follow a student t distribution. And that's only going to happen if one of two things: the population is normally distributed or the sample size is greater than or equal to 30. So in this case, we're able to do the test because the population itself was normally distributed, even though our sample size is small. Okay, so either this has to be greater than or equal to 30, or the population has to be normally distributed. If neither one of those things happen, you can't do this test, okay, because your sample means are not following a distribution that we know anything about. So we're good to go on the test because the population was normally distributed. The next thing you might think about is, do we know the standard deviation of the population or not? If we don't know it, we're going to use a t-test. If we do know it, we're going to use the regular z-test. And in this case, sort of a giveaway is that they told us what the sample standard deviation was, right? We don't know the standard deviation of the population. So we're going to use a t-test in this case. All right, so whether you draw the picture or not is going to depend on how many you've done and whether or not you can draw the picture in your head. But the picture always kind of looks the same. Here is a t-curve. we're going to say it's centered at the mean, right? And its spread. And its spread is given by the sample standard deviation divided by the square root of sample size. We're going to calculate a test statistic, T, and then we're going to find this area. And we're going to say, did I do that right? Greater than or equal to. Yeah, so it's a one-tailed on one side. And then we're going to find this area, and we're going to say, what's the chance I fell over here? Okay, whoops, no, I think I have it upside down, don't I? We want to know, is it greater than or equal to? And so we want to say, this is low, right? This is too small. So small's on this side. And we want to say, is it small enough, right? Is it small enough to reject the null hypothesis? All right, let me get my test right here. Okay, there we go. So 19,000 is going to be less than our mean. And then we want to know, is it enough less that this provides enough evidence to reject the null hypothesis? Okay, so there's the picture. Doesn't take very long to draw the picture. So I probably would. If I was looking for some partial credit, I definitely would. If I was doing 50 homework problems in a row, I might, but you know, by about the 20th one, I might just jump right to the calculator. That's going to be sort of up to you and your level of comfort there. And so here's what we do. We calculate this area. So I would say, I would just say T CDF, right? It's the area to the left, 1E99. It's going to be the area to the left of our test statistic, right? So we have to find out where our T is. So what is our T? Where is it? 19,189. The mean was 21,000. And the standard deviation was 2950 divided by the square root of the sample size, which is 14. And this is going to give us the area. So let's see if I can calculate that. I've got distribution. I'm going to go to a TCDF. Okay, I'm going to go minus 1E99. I'm going to say, what was it? 19,189, 21,000, 2950 divided by square root of the sample size, which was 14 cars. Uh-oh. And I get an error. How come? And you'd say, well, I don't know. That's a good question. Student T-curves, right? Student T-curves require that we have a number of degrees of freedom, right? They're different for the different sample size. So I'm going to have to tell it the number of degrees of freedom. So in here, I'm going to have to put, before I close it off, the number of degrees of freedom. 13, I think that's all I need to do. Oh, it's still wrong. Clear. How come we're getting this error? That's a very good question. Let me think about that for a minute. I don't use this calculator that often. All right, fine. Let's just cut to the chase. And while I'm thinking about why this is giving me an error, let's just let the calculator do all the work. Okay, so to do that, we're going to push stat. We're going to go over to test. We're going to come down here to a t-test. That's number 2. We're going to do it from stats. We're going to test that the mean was 21,000. We're going to get a mean of 19,189. The sample standard deviation was 2950. The sample size was 14. And we want to test if the mean is less than, right, less than 21,000. And we want to calculate it. Bam. Okay, so if we just, instead of doing it kind of one step at a time, if we just let the calculator do the whole test, it's going to come up with a t of negative 2.3 or so. So the question is 2.3 over there far enough? And the answer is, well, a p-value for this would be 0.019, or about 0.02, or 2% of the time you would get a p-value this small. We were supposed to be at the 5% significance level. There it is right there. So since 2%, right, is less than 5, we would say that 19,000 is small enough to be statistically significant, and we would reject the null hypothesis in favor of the alternative that, in fact, you know, the prices of cars were less than that. Okay. I'm wondering about why our other didn't come out right. I think maybe we have to calculate the test statistic ourselves for this TCDF. So for our TCDF, right, I let it calculate it itself here, but I think that you might have to actually put the test statistic in. So we might have to normalize ourselves. So to calculate this test statistic, we're going to say the value, right? The value minus the mean over the standard deviation. I thought it would do this calculation for me, but maybe it can't. Okay, and we'd say 19,189 minus the 21,000. Okay, we would divide by the sample standard deviation, 2950, divided by the square root of the sample size. That looks pretty good. And we get a test statistic of minus 2.297. So that should look pretty familiar. That's the same t that the calculator got when we did the t-test. So if you're doing it by hand, you should be getting the same numbers, okay, which we did. And now to find the area, right, to find the area, we're going to go to distribution. We're going to go TCDF. You know, some of the newer calculators, when you select the option, tell you what the parameters are. So it tells you what the order is of the arguments that you need to put in here. That's actually really kind of nice. Mine's old. And so if I forget what they are because I don't do it very often, or because I keep jumping back and forth between different pieces of technology, you can always just do this. This is what I would do. I would screen share with you. Where are we? Screen share. Yeah, no, I'm not there anymore. Okay, and type in this TI84 TCDF. Okay, and then it's going to say, how do you do a TCDF on here? Or maybe the very first thing from developer, it's going to say TCDF, blah, 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 p-value, right-tailed. I don't know which one's going to be the best. This one, finding p-values on a TI-83-4, right? The calculator takes TCDF lower, upper degrees of freedom. In other words, in this case for the, it doesn't know how to do this calculation of the t for you. It'll do that for a normal curve, but it doesn't look like it does it for a t curve. So we're now going to put in this 1E99. Then we're going to put in our t value that we found, which was minus 2.297. Can you see that still? Come on, focus. Yeah, it's close. Okay, and then we put in our degrees of freedom, which was n-1, boom, and it says our p-value right, is equal to 0.0194, or just a little less than 2%. Okay, the same calculation that the calculator got when we did the whole test. Since this is 2%, we were working at the 5% significance level. We would reject the null hypothesis and say that the test is statistically significant. In other words, car sales were a little bit less than the 21,000 that were projected. I'm kind of thinking that we did some of the work here, right? In our case, we did, you know, some of the work by hand, and we did some of the work by calculator. Right? I'm kind of thinking that, right? I'm kind of thinking that we better fix this. I'm kind of thinking that might be a good idea for you to show, you know, to show your work a little bit. There we go. Okay, of what you did. So either explain it in words, or, you know, maybe write a few things down if you, you know, if you want to go for some partial credit. That's kind of the plan. All right, so there's a hypothesis test where we use a student T-curve, and we use the sample standard deviation to approximate the standard deviation of the population. And it was also playing with the technology a little bit. The last few times that I've taught this class, I taught it using a TI. And so, but it's been a little while ago, you know, and so I still like using the calculator. It seems comfortable to me. Other people, you know, I've heard, like Michael Sullivan, who writes, you know, who's written a stat book. He says, don't use that anymore. There's better tools. And then he usually uses StatCrunch or something else. You're certainly welcome to use Desmos, StatCrunch, Excel, the calculator, a different calculator, or if you really want to go old school, the tables in the back of the book. Any of those ways of calculating the areas are fine. But what I recommend is that you try a couple of different technologies, and then maybe settle on one and then use that one, so that you aren't confusing, you know, which buttons to push on which one, like I just did in this problem, right? So either use a bunch of them a bunch of times so that you're really comfortable with a lot of them, or try a few, pick the one you like, and then kind of settle on using that one. That's what I would recommend. Okay, that's all I have for you today. A couple of examples. The homework then is going to be a bunch of examples for you to try. So you go do a little hypothesis testing in the homework. And I think that hopefully now at the end of the week, you should be pretty comfortable with, you know, with this chapter 7 and hypothesis testing. We're going to wrap it up on Tuesday with any questions that you might run into over the weekend. And then we're going to start our last chapter, chapter 9. It's on correlation and regression. So that'll be our last topic. Before I let you go, I want to ask one more time if there's any questions or things I can help with. I'm getting a couple of no's from people I can see, right? I'm getting a couple of no's in the, at least good for now's in the chat. So if you do run into some problems over the weekend, I will be checking my email from time to time. You're also welcome to come to office hours tomorrow. I'll be online at 10. So if you want to just drop in and get some one-on-one help, or just kind of go through a couple of problems together, I'd be happy to do that with you. Otherwise, have a great weekend, and we will come back next week with just 2 weeks left and get things wrapped up. All right, that's it. Have a great weekend, everybody.
All right, thank you.
Thank you.